In this video I'd like to do some more examples using the ideas, the concepts around force, but also talk about momentum and do some examples involving momentum. So first of all, just quick definitions in terms of rules for both of those. Momentum is the product of mass and velocity. So the momentum of an object is dependent on its mass, which is a scalar quantity, but also on its velocity, which is a vector quantity, and therefore momentum can be thought of as a vector quantity as well. And we're already familiar with the idea that the force, the resultant force, is going to be the mass times the resultant acceleration, and that is also a vector quantity because acceleration is a vector quantity. Let's talk briefly about units that we use when considering these quantities. So the units of mass, the standard units are kilograms, and that means that if we're going to multiply mass times velocity using standard units, then for momentum we're going to get kilograms meters per second, because velocity is measured in meters per second. And when it comes to force, well, newtons are the standard units of force, but newtons are really just a way of saying kilograms meters per second squared, because that's what we get if we multiply mass times acceleration, and acceleration standard units meters per second squared. Now, just before we go on to talk about some examples, we should maybe clarify that because typically when we're working with these sorts of problems, we're really just talking about motion in a straight line, and so therefore it's generally sufficient to just use a plus or minus. So plus or minus to indicate the direction of momentum and or force, rather than needing to use vector component notation all the time. So rather than needing to use i's and j's all the time, because we're just straight line motion a lot of the time, we can just use plus and minus. And just be clear about which direction is positive and which direction is the negative direction for motion. Alright, finally, the idea of friction. Friction, the frictional force, and here I'm not writing it as a vector, so I guess I'm just talking about the magnitude of the frictional force is equal to mu times n, where mu is the coefficient of friction of the surface. So obviously the sort of rougher a surface is, the more resistive it's going to be. And if we try and slide something across a very smooth surface, there's not much friction from the surface. If we try and slide something across a very abrasive or rough surface, there's a lot of friction from the surface. So that's one of the things that friction is dependent upon. And the other one is the normal force of the surface on the object. So how much, basically how heavy the object is, how much weight is bearing down, the surface is applying that force back up against the object, and that is also contributing to how much friction there is. So if you have a very light object and you're trying to move it across a surface, there will be less friction than if you're trying to move a very heavy object across the same surface. Okay, let's get in and consider some examples here. We'll start off with this one here, exercise 14. Now find the momentum of each of the following. Let's just do part B. The momentum of a mass of 300 grams moving with a velocity of 3 centimeters per second. So here we're really just talking about the magnitude, aren't we? We don't need to worry about the direction because it's just whatever direction it's moving in. So we can just say momentum is equal to mass times velocity. Now, so that we can get our units correct, we should say that 300 grams is 0.3 kilograms, and we're multiplying by a velocity of 3 centimeters per second, which would be 0.03 meters per second. So really the only thing in this question is getting our units right, and then if we multiply 0.3 by 0.03, well, that's 9, isn't it? So 3 decimal places, and kilograms meters per second. Alright, so there's an example just calculating basic momentum. Likewise with this question, let's just consider one part. So we're being asked to find the change in momentum when a body of mass 10 kilograms moving in a straight line changes its velocity from 6 meters per second to 3 if we do part A there. So in part A, the change, I'll use sort of delta there to indicate change. Change in momentum is going to be the final minus the initial. That's what we do with any change, isn't it? Change in velocity, change in acceleration. So that's going to be m times, let's say, velocity final minus m times velocity initial, which is just going to be, what's the mass here? 10 kilograms. Final velocity is 3. The initial velocity was 6. So that's going to be negative 30 kilograms meters per second. The fact that it's negative 30 is indicating that it's a decrease in momentum rather than an increase in momentum. Alright, we'll consider a couple more examples as well. In this one here, we've got a parachutist of mass 75 kilograms whose parachute only partly opens. It's always a bit disastrous. Accelerates downwards at 1 meter per second squared. That's not good. What upwards force must her parachute be providing? Now, I guess if you think through this, you'd say, well, if she had no parachute, then she'd be accelerating downwards at 9.8 meters per second squared, wouldn't she? Essentially. I mean, there'd be some resistance, I guess, from her own clothing and body and so on, but essentially she'd be accelerating downwards at 9.8. So definitely the parachute is doing, a significant job, but still, if you're accelerating downwards at 1 meter per second squared, you're still going to get up a fair bit of speed before you hit the ground, aren't you? So let's think about, let's just draw an object here to represent the parachutist, and let's let P be the force that's being, the sort of resistive force that's being applied by the parachute. So we'll call that the resistive or resistance force of the parachute. Spell parachute correctly. So that's acting in that direction there, isn't it? And let's maybe call that positive direction that way. Downwards, what's acting downwards? Well, downwards is just mass times g, isn't it? So 75g is the force that's acting downwards on the parachutist. So the resultant force, well, that comes from P minus 75g, and that's actually, let me write that as, first of all, P minus mg equals ma. So the resistive force of the parachute upwards, take away the force of the of gravity on the parachutist downwards, is going to give us the resultant. And so then we can say, well, therefore P minus 75g is equal to 75 times negative 1, because she's accelerating downwards. So therefore P is equal to 75 g minus 1, which is what, 75 times 8.8, and therefore P is equal to, grab your calculator for that one, 660 newtons. So that's the upwards resistive force that her parachute must be providing, but unfortunately it's probably not enough to prevent a rather nasty end. Okay, final example for this video. We've got a particle of mass 16 kilograms, which is being acted on by 3 forces, F1, F2, F3, measured in newtons. F1 has these I and J components, F2 has that one. The acceleration of the particle is that. You can see that's a vector quantity, and we're trying to find F3. Okay, so first of all, let's say that the resultant force is equal to mass times acceleration. Let me just move this over here a little bit, because what we're going to fit in there is to say, therefore, the sum of these three forces is equal to the mass times acceleration. So that's what, 16 kilograms times the acceleration is 0.6 I. Okay, let's write down or include the information that we know. So F1 is negative 10I take 15J. F2 only has a J component of 16. F3 is what we're trying to find. And if we wrote this in component form, what would that be? 9.6 and 0. Alright, so F3 has got to be equal to, and we could take 9.60, and let's take away the sum of these here. So take away, what's that, negative 10 and positive 1. So take away negative 10, 1, which is equal to, what's that, 19.6 and negative 1. So F3, if we write it in the same form as the other two, is 19.6I minus J, and we could say newtons there, since we know they're all measured in newtons.